So, thank you, David. Thank you, Aish, and thank you all for coming. So I have a confession to make. I'm not an architect. I'm originally an aerospace systems engineer, but I have spent 20 years working in an architectural practice. So, apologies if I've got a little bit corrupted by that experience. So I've been asked to be a little bit provocative and challenge. I also understand that the audience is perhaps more technically aware than I was led to believe, so I maybe be preaching to the converted, but hopefully raise some interesting points for you. So we have an interesting challenge in our industry compared to other engineering sort of disciplines, that most other disciplines are doing mass production with all the benefits that you can invest in upfront R&D. You know, we are essentially in our industry, in the architecture industry, are doing mass customization. So you know, that is lovely if you can do it, but we have a much more tricky challenge, I would say. But at the same time, we shouldn't fall into the kind of the trap of saying, let's just do the very basic. We really should be pushing things. So a quote from a very one of my favorite authors. You know, I wanted to talk about sort of how we use technology and the fact that the future is maybe already here, just not evenly distributed. If I was to ask you what CAD system, what BIM system, what engineering software BID used to create this building, you know, he certainly wasn't using any of the packages we use today, but he was certainly doing computation, albeit analog computation. Work on sort of computation at Foster's precedes me. This is amazing work done by our colleagues at Borough-Apolds and at Bath University. You know, some very elegant integration of geometry and structural optimization and buildability. So these tools have been around for a very long time, although they've been very specialized. This is one of the first projects I worked on. This is the refurbishment of Dresden Railway Station. So this was an interesting example where we were working with Apolds. They were doing a great job, but the cycle time was still too long. So we actually wrote a custom integration between MicroStation and a DOS-based form-finding bit of software called MCM. And we could go round the loop in maybe a sort of a half-day cycle rather than a one-week cycle. So, you know, if you never have to reverse engineer a file format, you'll be very fortunate. But it allowed us to do certain things that were very powerful at the time. You know, with Swiss Re, again, a very odd example of computational design. You know, the tools we were using were Excel. You know, what we were outproducing was very crude, but it allowed us to do things that at the time were very hard to do. You know, integration time was very limited. You couldn't even exchange data properly between MicroStation and AutoCAD. You know, which is why we had this sort of very simple geometric definition. But it allowed us to essentially mass customize and create a building that I think still stands the test of time. This is Casa Futura. This is a wooden chalet we did in Switzerland about 15 years ago now. Again, a very challenging site. You could only build on the site half the year because otherwise it was snowbound. You know, everything is custom. So again, completes a digital model, pretty much entirely kind of made in the factory, brought to site, installed. Yeah, so off-site manufacturing is it's not a novel thing. It allowed us to do things that we couldn't otherwise have done. Even with the Smithsonian, sort of in a way the sort of son or daughter of the British Museum, but actually a much more challenging structural problem. We could only put supports down onto these. I'm trying like laser pointer working. No, not going to work. These 8 columns. No load could be put on the existing building. For cost reasons, we couldn't have triangulated glass. So the whole thing had to be much more rationalized, so with a much smaller budget. So our strategy was to rather than having a massive team to try and do this, have a very small team of architects working with programmers, myself included, and generate the entire roof with one program. So this is 5,000 lines of code, 57 parameters, and generating a huge number, I think 250 options in the end, and lots of geometry. more critically, this allowed us to work very closely with our structural engineers, again, Apple's in this case. So rather than having a very laborious process of exporting a CAD file, then reading it in, we were exchanging very lightweight representations, and they could very quickly analyze it. So again, getting that cycle time down to a day or so. I think also what was critical is the level of detail we could go to. So we could have really generate down to a very high level of detail all the geometry of the building, directly send that to fabrication, again, lots of off-site kind of assembly of components, and create something which was at the time pretty complex, but at a very low cost and with a much higher degree of certainty. And more recently, we've been scaling things up. So this is Mexico City Airport. Hopefully, we'll return to us at some point. But this is a very good example of combination of computational design, computational BIM, a very high level of detail down to all the services, the structure, a completely integrated structural system. This gigantic space frame with sort of 160-meter clear spans. Again, to try and do this without computation would be extremely hard, and it was probably one of the most challenging projects we've worked on in the office. So these tools have allowed us to do things that we couldn't have done otherwise. Some of them have been extremely crude, but one should not underestimate their power. It's also key to say it's about people as well. These tools are not magically going to solve your problems. You need a room of people. You need your architects, your structural engineers, your environmental engineers, your project managers, your clients. Everybody needs to be integrated as well. So, one equation. So force is mass times acceleration. So it's all very well being incredibly fast, accelerating ahead of the curve. If you have not got the mass behind it, your effective force is going to be quite low. So one of the challenges we've had is, how do we go from an environment like this? This is our office 30 years ago, with I think you can see about 6 computers and lots of paper, through this, just when I sort of started. And some of you, I'm sure you remember this, very kind of hybrid workspace. We're now at this level, so a lot less paper, a lot more physical, a lot more screens, a lot more physical models. Interestingly, the question is, what comes next? What is it going to be? A screen in 5 years' time? What will it mean to kind of have window? These sort of, what will the office environment be like? How will we work? I think the interesting news is, we are a large organisation. A lot of people coming out of university have some good digital skills already, but it's how do you correctly harness them? How do you make people aware of what can be done? And also, how can we improve the sort of technology? The technology has improved a lot in the last 20 years. It still has a long way to go. So I want to talk about a couple of things that we've been working on internally for a while that maybe help advance. So one of the biggest challenges, I think, is that technology can be very unfriendly. There's still, in some cases, quite a hard boundary between people and technology. And we've done a lot of work over the last 20 years trying to break that down, particularly on the interface side. So these are some examples of tools we've written that hopefully are more intuitive. So on the top left is a very early augmented reality multi-user design system. So one can have the sort of natural conversations that one's always used to, but actually edit a digital model floating in front of you. A sort of cruder implementation, perhaps to the top right, this is a physical model which we are scanning in real time, we are analyzing in real time, we're projecting the results back onto it. Again, it seems to allow people to sort of engage with the process much better. Lots of work on virtual reality. Our current sort of implementation of these tools is a bit of software called Sandbox. So this is a sort of cross-platform tool for early-stage conceptual modeling. We support a whole bunch of different interfaces, touchscreens, virtual reality, augmented reality, iPads. So really trying to make these tools available to people in environments they feel comfortable with. Also key, it is a multi-user system, so it's not just, you're not just sort of doing it by yourself. and we are trying to decouple the interface from the analysis. The analysis in the main runs in real time, or near real time, so you're getting that very, very fast feedback. And what we're finding is it is leading to much better conversations, both internally but also with our clients. And we're getting some users at all levels of the organisation, which is quite nice to see. I also want to talk a bit about, I've talked about sort of trying to break down the barriers between sort of people and software. We also have possibly a bigger problem of barriers between bits of software. Between bits of software. For all the wonderful statements about IFCs. So this is a bit of software we've written called Hermes, which allows us to link different bits of software together dynamically. In this case, we've got a scenario. We've got a sort of very simplified client-facing tool in Unity. There's Dynamo running connected to Revit in the middle, and then Rhino and GSA running side by side. What would also be good if it ran is the movie. Let's see if this wants to play. If not, I'm going to try and... Oh, okay. So the nice thing is basically we're trying to design a tower here somewhere in China. So we can look at the views at different heights. As we do that, we can basically generate a floor plate in Dynamo, size some columns through Rhino, send that back in real time into this client-facing tool, and then evaluate, what's the impact of this column sizing on the views at different heights. And then, being architects, they want to change the shape. Okay, what does that then do to the space planning grid? They throw it, and comes into GSA. I'm sure all of you are sighing at this point, saying, "What the hell have you done to my structure?" But it's okay. Diagrids are a good thing. So we can then send that back over the wire, and then there's the result. So this is happening in real time or near real time. These picture packages are not designed to talk together, but we've sort of made them talk. The nice thing is this can work locally on a single machine across multiple machines. We've been using this for some of our consultants as well. So this is really trying to be a sort of universal translator. And this is our implementation of an idea. There are quite a few other implementations of this idea out there. I think we'll be seeing some more mentions of these. I think my strong desire is that we try and agree some open standards on this, because I think everyone's got some very lovely implementations of this idea. It would be good to sort of push it all together. But the key thing here is you're breaking down silos between bits of software and ideas which should not be in silos. The other thing we've been looking at is, can you break down the barrier between sort of human intellects and computer intellects? So can you use humans? Can you use computers to help you design and be more creative? So this is a project we were doing, looking at trying to do a sort of master plan generation. We're looking at daylight, solar gain, views towards nearby sort of water and mountains, and also drugs. So we essentially have written a genetic algorithm which will try and optimally place these elements, and we've linked it up to essentially a supercomputing system we've developed in-house, which is essentially using most of our machines to run multiple options, analyze them, crossbreed them, and refine them. So probably testing out sort of hundreds of thousands of options overnight to create a range of possible cities that could work based on these criteria. Done similar things at building scale. So here we're looking at sort of views, daylight, basic structural considerations, I would say. So interestingly, some of the massing options on the right are very good for views, but perhaps less good structurally. But the key thing is you could then converge on a massing, as you can see on the left, which arguably is pretty buildable. And then classic things like sort of sizing kind of columns to minimize material usage. We've also started using, so again, this sort of distributed computation system we called Hydra to do some material optimization. So in this case, I'll please show you the next movie. we are trying to simulate the behavior of essentially adaptive materials. So materials that will respond to environmental conditions. This is a very non-linear behavior. Trying to simulate is very hard. So essentially we've combined a non-linear solver with a neural net to try and learn how to predict if you want this desired outcome of material behavior, what is your input kind of composite layup. So these are very powerful tools. They need to be used quite wisely. Apologies. Another key thing which we as an industry, I think we should do a lot more of is evidence-based design. So actually checking what we've built actually correlates with what we've simulated. The good news is that sensors are becoming much cheaper and our ability to process that data is becoming much better. This is a sort of, not a structural problem, but this is a noise monitoring system we put together using a very low-cost bit of kit, so Raspberry Pi, a microphone. Here we're monitoring noise across London with very low-cost devices, correlating with aircraft. The key thing is, this would have, sort of 5 years ago, 10 years ago, this would be a very expensive thing to do. Now we can do it at, say, £100 per unit. Sensors are getting radically cheaper. There should be no excuse not to fully sort of instrument up one's buildings the same way as aircraft designers do or car designers do, and use all that data to inform ourselves. So, it all sounds wonderful, but there is a risk of this. Any sufficiently advanced technology is indistinguishable from magic. So a lot of people might assume technology is a magic panacea, it'll solve all your problems. For the record, I like pasta a lot, but there is a thing as too much spaghetti. I'm sure some of you have probably seen this sort of thing. Some of these tools are wonderful, but they need to be used very carefully. They need to be directed well. The same goes for analysis. It is very easy to be seduced by colors for designers, or CFD is sometimes known. In terms of training the next generation, critical thinking is pretty damn critical. And if you think it's bad with just simulation, wait till we get to AI. A lot of these systems are black boxes. We don't really know what's going on inside them. That concerns me, to be frank. I think we need to be even more critical of how they are functioning and how we can prove their results. So those are one sort of challenges. I'd like to suggest perhaps we also have two bigger challenges facing the industry. So one is, buildings have always helped sort of fulfill Maslow's sort of needs hierarchy. At the very basic level, they provide shelter, they provide sort of ventilation, safety. Over time, they have become bigger than that. They become spaces to inspire, ways to create experience. And they can, using one of our projects as an example, but they can really inspire people. They can create spaces where people can be creative, that create pleasure. And it is a big responsibility. This is Beijing Capital Airport, Terminal 3, which we worked on and opened about 11 years ago now. By my rough calculations, about 700 million people have been through this airport. So that is a very large responsibility to create that sort of experience. And historically, only a building could create that sort of experience at that sort of scale. But that is beginning to change. So I've been involved in sort of virtual reality research for more than 20 years. I'm usually pretty good at telling what is real and what is virtual. Until a few years ago, I tried out this. This is a VR experience where you walk on a tightrope between the old Twin Towers in New York. Someone actually did this for real when the World Trade Center first opened in the 70s. So you think, okay, fair enough. I'm in a conference center somewhere in California. I've got to walk maybe the length of this room. I have my headset on. It's fine. I have some headphones on, with some wind noise. I have a fan blowing on me, and on the floor is a plastic strip, wide. Fine, it's all good. I've been doing VR for 20 years, nothing to fear here. So I walk up to the edge of the tower. I cannot do it. And I'm like, Francis, okay, you're in a convention center in California. Yeah, this is a simulation. This isn't me, but this is pretty similar to what I was feeling. I was told actually about 90% of people couldn't actually do this, which is quite scary. And these are sort of computer graphics professionals. So if it can trigger a automatic response in me, could probably do it in most other people. It gets weirder. A short while later, I happened to be sitting on a boat off the coast of California, beautiful sunset, but I was thinking, like, this doesn't quite feel right. The water's a bit too glassy and the sunset's a bit too glossy, and it's like, the virtual has become real and the real has become virtual, and that's quite a scary thing. So maybe one might say, with Podges Le Corbusier, a holodeck is a machine for living in. It gets even more interesting if you consider augmented reality. So, already this is proving to be an interesting tool to sort of combine the real and the virtual. This is an example looking at sort of seeing through walls, looking at sort of structure or services. We're doing an office. It gets also interesting in terms of collaboration. So this is a testing we were doing. So I'm standing in one of our meeting rooms. My colleague here is virtually joining me from another part of our campus. We're both looking at this shared model. We're in an environment we know, but I'm interacting with somebody who is not physically there in a very intuitive fashion. Now, that is nice for us, but consider the impact on lots of other ways of doing business. Actually, do I need to fly halfway around the world for a 2-hour meeting? If I can get now, what is the implication on our buildings, on our transport systems, if you could do this effectively? And also, it's not just about headsets. So, again, yours truly, looking up at this very nice, Mediterranean sky, out this skylight. I'm squinting. It's bright. It's a very nice environment. The problem here is I'm actually 2 floors underground, and that is not a real skylight. This is a virtual skylight, but it's triggering the same responses in me as a real one would do. So if you think about the effort we put into allowing for natural daylight, which is a very good thing, it's a very good thing for human beings. Actually, technology is coming that will possibly remove the need for that. Likewise, maybe displays getting to the stage where you could do virtual windows. You could have my kind of California sea experience from the comfort of your own office. So buildings are very expensive. Land is very expensive. I believe that AR and VR will pose quite a big challenge to the way we deliver buildings. Actually, if I can deliver a lot of the top of this pyramid, does the building just need to provide the bottom couple of layers? In which case, just give me a well-insulated box and I'll have done with it. So that I think, is an interesting challenge, but we face. Possibly a bigger challenge is we only have one of these. This is a very small blue and green marble in a very big universe. As an aerospace engineer, I'm very happy to see people looking at sort of colonizing Mars and other places, but within our lifetimes, that's unlikely to be a major factor for most of the population of the planet. Most of you, I hope, are familiar with the idea of one planet living. Currently, we are not doing that in any major way. These are, the UK is not a good example. We're using the resources of 3 planets per sort of, on average. It is getting quite a critical problem, and as engineers, as architects, we have a strong duty to try and fix that. So I think the good news is that through computation, one can optimize, one can be much more efficient in one's uses of materials. So we've started some work with Cambridge and Bath universities on some optimal kind of creation of concrete. We've been doing work with Cranfield on metal printing. All these technologies are, we've been working on some of these things for a very long time. They are getting to production levels of quality. and it will, I think, radically change in terms of what we can build and how efficiently we can build it. I think robotic assembly, this is not a fully automatic robot, this is Swiss 3 going up, but robotic assembly as well could really improve the way we can build things. We should also remember that we actually have, in a way, unlimited energy. The sun creates a huge amount of energy. We do not use 1/100th of what actually lands on the Earth's surface. So actually, that is free. We should use more of that. And I also think we should tap into nature. Hundreds of years ago, people were growing trees in sort of, and forced them to grow in certain shapes to create the sort of ribs for ships. That took 40 years to grow a ship. Nature builds some pretty impressive structures. I think there are some things we could do to sort of work with nature. So perhaps in the future, a building will be a self-assembling robot for living in. So I've given some ideas there. I think we really need to integrate more. There's a lot of challenges to face. We need to be working in a much more integrated fashion. I think we need to differentiate more. We need to differentiate from other industries to say, actually, this is why we are adding value. This is how we're going to meet the needs of our society and of our planet. So thank you very much.